From the deepest stillness of a desert night, humanity has always looked up. We have gazed upon a celestial river of pale, shimmering light, a luminous smear painted across the velvet blackness of the cosmos. Ancient cultures saw it as a pathway for souls, a river of milk, a divine serpent winding its way through the heavens. For millennia, this was our universe, a familiar celestial canopy. But this comforting familiarity is a grand illusion. That gentle, ethereal glow is a spectacle of unimaginable violence and scale. It is the edge-on view of our own home, a colossal spinning disk of stars, a stellar metropolis containing hundreds of billions of suns. We are not at the center of this spectacle, but adrift in its quiet suburbs. This city of light, our Milky Way, is just one among trillions. Each point of faint, fuzzy light in our most powerful telescopes is another island universe, another complete cosmic dominion. And the truth about these majestic structures is far stranger, more complex, and more profound than our ancestors could ever have dreamed. For a surprisingly long time, we did not even know they existed. In the early 20th century, the greatest minds in astronomy were locked in a fierce battle of ideas. A great debate. The central question was the very scale of existence itself. Were the faint, swirling nebulae observed through telescopes merely clouds of gas and dust within our own Milky Way? Or were they, as some audaciously proposed, distant island universes, entire galaxies just like our own, separated by gulfs of unimaginable emptiness? Imagine the scene. 1920, the Smithsonian Museum of Natural History. Two intellectual titans, Harlow Shapley and Heber Curtis, stand before their peers. Shapley, armed with his work on globular clusters, argued for a single, vast galaxy. He had radically expanded the known size of the Milky Way, dethroning our sun from its central position. To him, it seemed inconceivable that anything could exist beyond this colossal structure. The so-called spiral nebulae had to be local phenomena. On the other side stood Curtis, a proponent of the grander vision. He pointed to the sheer number of these spirals and the appearance of new stars, or novae, within them, suggesting they were incredibly distant and enormously large. He argued that our cosmos was an archipelago of stellar realms. The debate was brilliant, passionate, but ultimately inconclusive. The technology of the day had reached its limit. A definitive answer was just out of reach. Humanity stood at a cosmic crossroads, peering into the dark, uncertain of what lay beyond. The answer would come from a lone observer, high on a Californian mountain. Edwin Hubble, using the monumental Hooker telescope at Mount Wilson, the most powerful instrument of its era, dedicated himself to this profound enigma. Night after patient night, he photographed the great spiral in the constellation Andromeda. He was searching for a very specific type of star, a Cepheid variable. These remarkable stars act as cosmic lighthouses. Their brightness pulsates at a rate directly linked to their true, intrinsic luminosity. By comparing this true brightness to how dim they appear from Earth, one could calculate their distance with unprecedented accuracy. It was a painstaking, arduous search through countless photographic plates. Then, in 1924, he found one, a single, pulsing point of light within Andromeda. He meticulously calculated its distance, checking and rechecking his figures. The result was staggering, a number that shattered the old universe forever. Andromeda was not a nearby cloud of gas. It was nearly 1 million light-years away, a distance so vast, it placed it far, far outside the most generous estimates for the size of our Milky Way. Hubble's discovery was a revelation that echoed Copernicus and Galileo. In a single moment, the known universe expanded by a factor of infinity. Our galaxy was not the entirety of creation, but a single grain of sand on an endless cosmic shore. The strange truth began to dawn. The universe was not empty space with a single city of stars. It was a teeming, sprawling, populated expanse filled with countless galactic empires. This discovery opened the floodgates, transforming astronomy from the study of stars into the study of cosmology, the study of the universe as a whole. But as our telescopes grew more powerful, peering deeper into this new, grander cosmos, a deeper and more disturbing mystery began to surface. The galaxies themselves were not behaving as they should. According to everything we understood about gravity, pioneered by Newton and refined by Einstein, the visible matter within a galaxy, its stars, gas, and dust, should dictate its motion. Stars on the outer edges of a galactic disk, far from the dense central hub, should orbit much more slowly than the stars nearer the center. Think of our own solar system. Distant Neptune plods along in its orbit, while nimble Mercury whips around the sun at high speed. This is the expected, predictable dance of gravity. Yet, when astronomers pointed their instruments at other galaxies, they saw the impossible. The stars on the outermost fringes were moving just as fast as the stars in the interior. It was as if Neptune were keeping pace with Mercury, a flagrant violation of cosmic law. This bizarre observation was championed by the tenacious astronomer Vera Rubin in the 1970s. Working with spectrographs that could precisely measure the speed of stars, she and her colleague Kent Ford systematically surveyed galaxy after galaxy. The result was always the same: flat rotation curves. The outer stars were moving with a reckless, inexplicable velocity. To understand the sheer strangeness of this, imagine a colossal cosmic merry-go-round. The brilliant, shining horses are the stars we can see. According to the laws of physics, the horses on the outer rim should be moving slowly, in danger of being gently left behind. But what Rubin observed was a merry-go-round spinning at a furious, uniform speed. The horses at the very edge were clinging on for dear life, moving so fast they should have been flung off into the intergalactic darkness centuries ago. The fact that they were not that galaxies hold themselves together at all meant there had to be something else there. Something massive, something invisible, something utterly unknown. This unseen substance, this gravitational scaffolding, was dubbed dark matter. It does not shine, it does not reflect light, it does not interact with any part of the electromagnetic spectrum. It is a ghost on the cosmic stage, perceptible only through its immense gravitational influence on the things we can see. Vera Rubin's painstaking work was initially met with skepticism, a common fate for revolutionary ideas. But the evidence was irrefutable, and as more data poured in, the conclusion became inescapable. The universe we see, the luminous and beautiful architecture of galaxies, is just the foam on a vast, invisible ocean. Calculations revealed a startling truth. All the stars, planets, gas, and dust, everything we have ever observed, everything that makes up you and me, accounts for a mere 5% of the total mass and energy in the universe. Roughly 27% is this mysterious dark matter, an invisible substance forming vast, spherical halos around every galaxy. It is the true foundation of these stellar cities, the unseen anchor, that keeps their stellar populations from flying apart. The visible galaxy is merely the bright settlement built upon a continent of darkness. This discovery was a profound lesson in humility. We had just grown accustomed to the idea of a universe full of galaxies, only to find out that the galaxies themselves are mostly made of a substance we cannot see and do not understand. It is as if we had spent centuries studying the glowing lights of a city at night, only to realize the city itself is 10 times larger, built from invisible bricks, on invisible streets, populated by an invisible populace. The strange truth of galaxies is that they are fundamentally dark structures, lightly decorated with the stars that we mistakenly thought were their main feature. And the cosmic weirdness did not end there. As astronomers mapped the motions of galaxies on an even grander scale, they expected to see the relentless pull of gravity in action. The mutual attraction between all these massive structures, both visible and dark, should be slowing down the expansion of the universe that began with the Big Bang. It was assumed the expansion was either coasting or decelerating, perhaps destined to one day reverse in a big crunch. In the late 1990s, two separate teams of astronomers set out to measure this deceleration. They used a different kind of cosmic yardstick, type Ia supernovae. These are the spectacular explosions of white dwarf stars, and they are incredibly special because they always explode with the same peak brightness. They are the ultimate standard candles, visible across billions of light years. By finding these distant explosions and measuring their faintness, the teams could determine how far away they were, and by analyzing their light, they could determine how fast they were receding from us. This would allow them to map the expansion history of the universe. The expectation was clear. The supernovae in the distant early universe should appear brighter than expected, because the expansion was faster back then and has been slowing down ever since. But when the data came in, it showed the exact opposite. The distant supernovae were fainter than predicted. They were farther away than they should have been. The only way to explain this was if the expansion of the universe was not slowing down. It was speeding up. This was an observation so counterintuitive, so contrary to all expectations, that the research teams initially assumed they had made a colossal error. They checked their equipment, their calculations, their fundamental assumptions, but the conclusion held firm. Some unknown force, some form of energy inherent in space itself, was acting as a cosmic anti-gravity, pushing everything apart at an ever-increasing rate. This mysterious influence was named dark energy, and when the cosmic budget was recalculated, it delivered the final, humbling blow. This dark energy accounts for a staggering 68% of the universe. So now the full, bizarre picture emerges. Our existence is built upon a 5% sliver of normal matter. The rest, the overwhelming 95% of reality, is composed of dark matter and dark energy, two substances whose nature remains a complete mystery. Galaxies are not just islands of light in a passive void. They are luminous tracers in a universe dominated by unseen forces engaged in a cosmic tug-of-war. Dark matter pulls them together, building the grand structures we see, while dark energy pushes them apart, driving them towards an increasingly lonely future. And within the heart of these already strange structures lies another layer of enigma. At the center of almost every large galaxy, including our own Milky Way, lurks a monster of unimaginable proportions, a supermassive black hole. These are not the black holes formed from the collapse of a single star. These are behemoths, millions or even billions of times the mass of our Sun, compressed into a region smaller than our solar system. Our own galaxy hosts Sagittarius A*, a gargantuan entity 4 million times our Sun's mass, around which our entire stellar city silently pivots. For a long time, it was thought that these central black holes were simply cosmic drains, passively consuming anything that strayed too close. But we now understand that their relationship with their host galaxy is far more intricate and dynamic. They are not just tenants, they are co-creators. The formation and growth of a galaxy appears to be inextricably linked to the formation and growth of its central monster. This relationship is a delicate and sometimes violent dance. When gas and dust spiral into the supermassive black hole, they form a superheated, rapidly spinning accretion disk. This disk can shine brighter than all the billions of stars in the galaxy combined, creating a phenomenon known as a quasar, the most luminous objects in the universe. This process also launches colossal jets of energy and particles, blasting outwards from the galactic core at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the visible confines of the galaxy itself. This feedback mechanism acts as a form of cosmic regulation. The jets can heat up and blow away the gas in the galaxy, temporarily shutting down the birth of new stars. This prevents the galaxy from growing too large, too quickly. The central monster, a creature of ultimate consumption, paradoxically governs the lifeblood of its host. It is a bizarre form of symbiosis, a relationship between creation and destruction played out on a galactic scale over billions of years. The strange truth is that the heart of a galaxy is not a point of serene gravity, but a raging, powerful engine that shapes its own empire. The lives of galaxies are not serene or solitary. They are dynamic, violent, and defined by a history of cosmic cannibalism. Over eons, galaxies collide and merge in slow, majestic, and utterly transformative ballets. Gravity, the great sculptor of the cosmos, draws them inexorably together. As two galaxies approach, their mutual gravitational pull begins to distort their shapes. Long, ghostly tendrils of stars and gas, known as tidal tails, are flung out into the intergalactic medium. The elegant spiral arms are twisted and warped into chaotic, irregular forms. Despite the visual chaos, direct collisions between individual stars are incredibly rare. The distances between stars are so immense that the two stellar populations mostly pass through each other like ghosts. The real action is in the gas clouds. As the vast clouds of interstellar gas from each galaxy slam into one another, they are compressed, triggering a furious burst of star formation. For a brief cosmic moment, the merging galaxies light up with the fire of millions of newborn, massive blue stars. This is a starburst galaxy, a spectacular but short-lived phase in the merger process. Eventually, over hundreds of millions of years, the chaos subsides. The two galaxies coalesce, their stars settling into new, randomized orbits. Their central supermassive black holes will also spiral towards each other, eventually merging in a cataclysmic event that sends gravitational waves, ripples in the fabric of space-time itself, shuddering across the universe. The final product is often a new, larger, and more spheroidal galaxy, an elliptical galaxy, bearing the scars and the combined mass of its progenitors. Our own Milky Way is a product of such a history, built from the debris of smaller galaxies it has consumed, and our future is one of collision. The great Andromeda galaxy, our closest major neighbor, is currently hurtling towards us at 250,000 miles per hour. In about 4.5 billion years, our two majestic spirals will begin a celestial dance of destruction and creation. The night sky of a future Earth will be a breathtaking, terrifying spectacle as Andromeda grows to fill the entire horizon. The two galaxies will merge, their structures will be torn asunder, and a new, giant elliptical galaxy dubbed Milkomeda will be born. The strange truth is that galaxies are not permanent fixtures. They are evolving, growing, and consuming one another in a cosmic cycle of death and rebirth. If we zoom out even further, beyond the scale of individual galaxies and their local groups, the strangeness intensifies to a level that challenges our very perception of structure. Galaxies are not scattered randomly throughout the universe like dust motes in a sunbeam. They are organized into a breathtakingly complex and beautiful pattern, the largest structure known to exist. It is called the cosmic web. Imagine the universe as a vast, dark space. Woven through this space is an intricate, three-dimensional latticework of filaments. These filaments are made primarily of dark matter, and they stretch for hundreds of millions of light years. Lining these filaments, like pearls on a string, are the galaxies. They flow along these cosmic superhighways, drawn by gravity towards the intersections. At these intersections, these cosmic crossroads, the filaments knot together. Here, matter is at its most dense, and we find the great superclusters, sprawling congregations of thousands of galaxies. Between the filaments of the cosmic web are the great voids. These are colossal, nearly empty bubbles of space, some stretching for over 100 million light-years. In these lonely deserts, galaxies are exceptionally rare. The universe on its grandest scale resembles nothing so much as a sponge or a neuron. The filaments are the axons and dendrites, the galaxy clusters are the synapses, and the voids are the empty spaces in between. It is a structure of profound elegance and staggering immensity, a cosmic nervous system within which all of creation resides. This web tells us the story of the universe's formation. In the immediate aftermath of the Big Bang, the universe was almost perfectly uniform, but there were minuscule quantum fluctuations in the density of matter. Over billions of years, gravity amplified these tiny imperfections. The slightly denser regions pulled in more matter, becoming the filaments of the web. The slightly less dense regions were left behind, expanding to become the voids. The galaxies we see today are the luminous blossoms that have grown on the gravitational skeleton laid down in the first moments of time. And now, with instruments like the James Webb Space Telescope, we are peering back through cosmic time to the very dawn of this structure. We are looking for the first galaxies, the first seeds of light that bloomed on the pristine, dark filaments of the young cosmic web. And once again, the universe is proving to be stranger than our models predicted. Webb is discovering galaxies that are far more massive, far more mature, and far more numerous in the early universe than we thought possible. These impossibly large early galaxies are challenging our fundamental theories of cosmic evolution. It seems the universe was in a hurry to build its great stellar cities, getting a head start that we are only now beginning to comprehend. Each new image, each new piece of data, adds another layer to the enigma. So we are left to confront the strange truth in its entirety. The beautiful band of light in our sky is a single stellar city among trillions. This city, like all others, is mostly composed of an invisible dark matter scaffolding. Its destiny is governed by a cosmic push and pull between this dark matter and an even more mysterious dark energy that is accelerating the expansion of space. At its heart is a creative monster, a black hole that both consumes and regulates. Its history is one of violent cannibalism, and its future is one of cosmic collision, and it exists as a single, luminous node in a vast web-like structure that forms the very architecture of reality. We stand on a small, rocky world, orbiting an average star in the quiet suburbs of one of these galaxies. We are the 5%, the luminous afterthought living inside a cosmic ghost. The universe is not what it seems. It is grander, darker, more violent, and more interconnected than we ever knew. The strange truth about galaxies is that they are not just collections of stars. They are complex ecosystems, crime scenes, monuments, and engines. They are the crucibles where the elements of life are forged. They are the keepers of cosmic history and the signposts pointing to our ultimate fate. And as we continue to gaze upwards, we do so with a new and profound understanding. We are not merely looking at distant lights, we are looking at ourselves, at our origins, and into the heart of the deepest, strangest mystery of all. The quest to understand is all that we have, and the universe, it seems, has no shortage of secrets to keep. Consider the atoms that make up your hand. Right now, as you hold this thought, trillions upon trillions of them are working in a silent, coordinated ballet. Carbon, oxygen, nitrogen, hydrogen. They are the architects of your bones, the couriers in your blood, the very scaffolding of your consciousness. You're a walking, thinking, feeling collection of these fundamental particles, a temporary vessel for matter forged in the cosmos. But have you ever truly asked the ultimate question of your own existence, not who you are, but what you are? And more profoundly, from where did that what originate? We often hear the poetic and powerful truth that we are stardust, and in a profound sense we are. The carbon in your DNA, the oxygen you breathe, the iron in your veins, these heavier elements were indeed cooked in the thermonuclear furnaces of stars that lived and died long before our Earth was ever born. They are the ashes of stellar titans scattered across the galaxy, to one day coalesce into new suns, new planets, and perhaps new life. It is a magnificent story, a cycle of cosmic death and rebirth that directly connects your life to the life of the stars. But it is not the beginning of the story. It is not even the first chapter. To find the true origin, the primordial source code for everything, we must look past the stars. We must journey back to a time before the first galaxy had even formed, before the first sun had ignited its brilliant fire in the cold, empty darkness of space. We have to travel to an epoch so ancient, so alien, that our very concepts of time and space begin to fray. We must go back to the universe's first breath, back to a moment of unimaginable violence and exquisite creation, a crucible that lasted for only a few hundred seconds. This is the story of that moment. It is the story of how the overwhelming majority of all the atoms in existence, the very atoms that would later build those first stars, were themselves forged. This is the story of Big Bang nucleosynthesis. It is the tale of the universe's first act of creation, a fleeting incandescent period when the fundamental laws of physics operating under conditions of extreme temperature and pressure wrote the elemental recipe for the entire cosmos. The results of this primordial alchemy are all around us, and indeed within us. The hydrogen that makes up the water in your body, the most abundant element in the universe, was almost entirely produced in this initial flash of cosmic fire. The helium that fills our party balloons and, more importantly, fuels stars like our own sun for billions of years is a direct relic of this same event. Our journey is not one of astronomical distance but of temporal depth. We will peel back the layers of cosmic history one by one. We will look beyond the familiar tapestry of swirling galaxies, past the intricate nebulae where new stars are being born today, and even past the epoch of the very first stars themselves. We are reaching for the bedrock of existence. We seek to understand the elemental blueprint from which everything else, every star, every planet, every living thing was eventually constructed. It's a story that begins not with a whisper, but with a roar that filled the entirety of space, because it was the entirety of space. A time when the whole universe was a furnace, a seething, undifferentiated plasma of energy and elementary particles hotter than the core of the most massive star. Imagine, if you can, a universe without structure. No up, no down, no light, no dark. There are no points of reference, no familiar celestial landmarks, because nothing has been built yet. There is only the universe itself, an expanding fireball of pure potential. In the first tiny fractions of a second after the Big Bang, this primordial soup was too hot for even the most basic components of atoms to hold together. It was a maelstrom of quarks, gluons, electrons, and other exotic particles, a chaotic state of matter known as a quark-gluon plasma. In this state, the very idea of a proton or a neutron, the building blocks of atomic nuclei, was impossible. The universe was a particle accelerator vastly more powerful than anything humanity could ever conceive of building, and it was the size of the entire cosmos. But the universe from its very first moment has been expanding and cooling. This inexorable process is the engine of cosmic evolution, and as the seconds began to tick away on the cosmic clock, this expansion brought about a profound change. At about 1/1,000,000th of a second after the beginning, the universe cooled just enough for the quarks to be wrangled together by the strong nuclear force. For the very first time, they were confined into stable trios, forming the first protons and neutrons. These are the particles that would come to define the atomic age. Yet for a short while, they were still swimming in a bath of radiation so intense that any attempt to bind together into something larger was immediately blasted apart. A proton might meet a neutron, their mutual attraction pulling them close, but a high-energy photon, a particle of light, would instantly sever their fragile nascent bond. The universe was a battlefield of creation and annihilation. For every potential partnership, there was a demolition. The cosmos was held in a state of suspended animation, filled with the raw ingredients for atoms but too energetic to allow construction. This was a critical waiting period, a cosmic standoff between the force that binds matter together and the sheer energetic fury of the young universe. The fate of everything we see today hung precariously in this balance. If the universe had stayed this hot, it would have remained a simple, uninteresting soup of individual protons and neutrons forever. If it cooled too quickly, the particles might not have had enough energy to overcome their mutual repulsion and fuse at all. The timing had to be perfect, and it was. Around 1 second after the Big Bang, the universe reached a milestone. The frantic sea of particles had calmed just enough. Neutrons, which are inherently unstable when left on their own, were now able to combine with protons without being instantly destroyed. But the true starting gun for nuclear synthesis, the moment the cosmic forge truly roared to life, had to wait for a specific thermal threshold. It happened when the universe was about 100 seconds old. The temperature had dropped to a mere billion degrees Kelvin. While that sounds impossibly hot, it was the perfect cool temperature for the first most crucial nuclear reaction to take hold. A proton and a neutron could finally fuse together to form deuterium, an isotope of hydrogen consisting of one proton and 1 neutron. This was the bottleneck, the Great Cosmic Dam, and it had just broken. The formation of deuterium unleashed a chain reaction that cascaded through the primordial plasma. The universe, for a brief and glorious window of time, became a single gigantic nuclear reactor. Deuterium nuclei were the essential stepping stones. Almost as soon as they formed, they were bombarded by other particles. A deuterium nucleus could collide with another proton, forming helium-3, a light isotope of helium with 2 protons and 1 neutron. Or it could collide with a neutron forming tritium, a heavy isotope of hydrogen, with 1 proton and 2 neutrons. These newly formed nuclei were themselves targets in this frantic cosmic dance. 2 helium-3 nuclei could slam together to create the grand prize, a nucleus of helium-4, an incredibly stable arrangement of 2 protons and 2 neutrons. Alternatively, a helium-3 could fuse with a tritium nucleus, also yielding the stable helium-4. All of this was happening everywhere simultaneously across the entire expanse of the infant cosmos. It was a symphony of creation conducted by the fundamental forces of nature. But this symphony had a time limit. The conductor's baton was the universe's own expansion and cooling. The window of opportunity for this fusion was closing fast. The density of the universe was dropping. The temperature was falling. The particles were moving farther apart from each other, and their kinetic energy was decreasing. The reactions which depended on high-speed collisions began to slow down. The cosmic forge was running out of fuel and losing its heat. By the time the universe was about 3 to 4 minutes old, the temperature had dropped below the threshold needed for nuclear fusion. The density was too low for particles to find each other reliably. The creative fire was extinguished. The brief spectacular era of Big Bang nucleosynthesis was over. It had lasted for little more than the time it takes to boil an egg, yet in those fleeting moments the die had been cast. The elemental composition of the universe was set for hundreds of millions of years. When the fire went out and the cosmic dust settled, what were we left with? The result was a recipe of profound simplicity and elegance. For every 10 protons that went into this process, the vast majority, about 8 of them, emerged untouched. They remained as individual protons, the nuclei of hydrogen atoms. This is why hydrogen is, by a huge margin, the most abundant element in the cosmos today. It is the primary leftover from the Big Bang. The remaining 2 protons, along with 2 neutrons, were locked away into the stable nuclei of helium-4. This means that by mass, the universe after this period was approximately 75% hydrogen and 25% helium. This prediction that about a quarter of the mass of all ordinary matter in the early universe should be helium is one of the most powerful and stunningly confirmed pillars of the Big Bang theory. When astronomers look at the most ancient stars and distant gas clouds, places untouched by later stellar processing, they find this exact primordial ratio a perfect match to the theory. It is an atomic ghost, an echo of the universe's first minutes imprinted on the cosmos for all time. But the story doesn't quite end there. The process was not perfectly efficient. Tiny, almost negligible amounts of the intermediate products were left over. A trace of the deuterium that started the chain reaction survived. A whisper of helium-3 remained. And most significantly, a minuscule amount of a third element was created. In extremely rare reactions, a helium-4 nucleus could fuse with a helium-3 nucleus to form beryllium-7, which would later decay into lithium-7. Lithium, the third element in the periodic table, was the heaviest element forged in any significant quantity in the primordial fire. And even then, its abundance was minuscule, about 1 lithium atom for every 10 billion hydrogen atoms. Why did it stop there? Why not forge carbon or oxygen or iron? The answer lies in a cosmic obstacle course. There are no stable elements with 5 or 8 nuclear particles. When a helium-4 nucleus collides with a proton, it makes lithium-5, which decays in a fraction of a sextillionth of a second. When 2 helium-4 nuclei collide, they make beryllium-8, which falls apart even faster. There was no stable bridge to get to the heavier elements. The universe in its rapid expansion simply cooled too quickly to overcome these gaps. The door to the rest of the periodic table was slammed shut. To build the elements of life, the cosmos would need a different kind of forge, one that could burn for billions of years, not mere minutes. It would need the stars. And so, As the era of nucleosynthesis concluded, the universe was left in a new state. The frantic creative blaze was over. For the first time, the cosmos was filled not with a chaotic plasma, but with a vast expanding and darkening cloud of atomic nuclei. A simple, predictable, and chemically uninteresting gas of hydrogen and helium, seasoned with a barely detectable pinch of lithium. This was the raw material, the primordial clay. This was the canvas upon which the rest of cosmic history would be painted. It was a universe of immense potential, but for now, it was dark. The nuclei were still adrift in a sea of electrons, unable to capture them to form neutral atoms. Light was still trapped, scattering off charged particles in a dense fog. The age of stars, of galaxies, of planets was still a distant dream, an unwritten chapter waiting for gravity to take the lead. Everything we are, everything we see, everything we can possibly imagine was built from this simple, three-element starter kit. The profound complexity of a spiral galaxy, the intricate chemistry of life, the staggering diversity of worlds, all of it had to emerge from this humble, elemental beginning. The journey from that hot, simple, uniform gas cloud to the rich, structured and vibrant cosmos of today is the epic of cosmic evolution. The stage was set, the ingredients were measured and mixed, but the story was far from over. An immense darkness was about to fall, a period that would last for hundreds of millions of years. How did this primordial gas, this ghost of the Big Bang's fire, begin to clump together? How did gravity, the patient architect of the cosmos, begin to shape this raw material, pulling it into the seeds of the very first stars and setting in motion the next great creative act? The universe had its blueprint. Now it had to begin to build. What if the entire universe, in all its sprawling luminous grandeur, was born with only 3 ingredients in its pantry? What if the breathtaking complexity of a spiral galaxy, the searing heart of a star, the delicate chemistry of life itself could all be traced back to a recipe of astonishing simplicity, executed in a cosmic kitchen hotter and denser than anything we can imagine? This is the story of our cosmic origins, not of planets or stars, but of the very atoms from which they are made. It is a detective story on the grandest possible scale, a search for the furnace that forged the raw materials of reality. And like all great mysteries, it begins not with an answer, but with the shattering of a deeply cherished illusion. For most of human history, and indeed for the giants of early modern science, the universe was a stage of eternal and unchanging majesty. It was the great static clockwork wound once and left to run forever. This was a cosmos of profound comfort, a fixed and reliable backdrop against which the fleeting drama of human life could play out. Even Albert Einstein, a man who had reshaped our understanding of space and time, instinctively clung to this ancient vision of a steady-state reality. When his own revolutionary equations of general relativity suggested a universe that was dynamic, that must either be expanding or contracting, he saw it not as a revelation but as a flaw, a blemish on the face of cosmic perfection. To stabilize his model, to force it to conform to the prevailing wisdom, he introduced a fudge factor, a mathematical contrivance he called the cosmological constant, a kind of cosmic anti-gravity, holding the universe in a state of perfect timeless equilibrium. He had created on paper a universe that would last forever because the alternative was simply unthinkable. But while the world's most famous scientist was working to preserve the status quo, a quieter, more unassuming mind was daring to embrace the unthinkable. Georges Lemaitre, a Belgian priest and physicist, a man who navigated both the rigorous world of mathematics and the profound mysteries of faith, looked at Einstein's unaltered equations and saw not a mistake, but a message. He saw a universe with a story, a universe with a past and a future. In 1927, working in relative obscurity, Lemaitre published a paper that contained the conceptual seed of our entire modern cosmology. He proposed a universe in motion, a cosmos born from a moment of cataclysmic expansion. He imagined winding the cosmic clock backward, watching as the galaxies we see today rushed back together closer and closer, until all the matter and all the energy in the entire universe was compressed into a single infinitesimal point. He called it the hypothesis of the primeval atom, a day without a yesterday. It was a staggering, almost blasphemous idea. It gave the universe a birth date, a moment of creation not from scripture, but from the cold, hard logic of relativistic physics. When Lemaitre finally had the chance to present his theory to Einstein, the great man was entirely unconvinced. "Your calculations are correct," Einstein conceded, "but your physics is abominable." The judgment was swift and devastating. Lemaitre's universe born in fire remained a mathematical curiosity, a theoretical ghost haunting the edges of accepted science. For theory, no matter how elegant, is not enough. To overthrow an idea as foundational as the eternal cosmos, you need more than equations. You need evidence. You need to see it. That evidence was being gathered piece by painstaking piece under the cold, clear skies of Southern California. Atop Mount Wilson, a steel leviathan, the 100-inch Hooker telescope, was pointed toward the heavens. Its operator was Edwin Hubble, a man as different from Lemaitre as one could imagine. A former lawyer, a decorated military man, Hubble was a meticulous, no-nonsense observer, a pragmatist who trusted only what his telescope and his photographic plates could show him. He was not hunting for the origin of the universe. He was simply trying to measure its scale to settle a long-simmering debate about the nature of the faint, hazy patches of light called spiral nebulae. Were they clouds of gas within our own Milky Way, or were they something more? Were they, as some had speculated, entire island universes, galaxies like our own, but lying at unimaginable distances? To solve the puzzle, Hubble needed a cosmic yardstick. He found it in a special class of pulsating stars called Cepheid variables. These stars are cosmic lighthouses. Their intrinsic brightness is directly linked to the rhythm of their pulsations. By measuring how fast a Cepheid brightens and dims, you can calculate how bright it truly is. And by comparing that true brightness to how dim it appears from Earth, you can calculate its distance with astonishing precision. Night after patient night, Hubble aimed the Hooker telescope at the Andromeda Nebula, searching for these flickering beacons within its swirling arms. In 1923, he found one, then another. His calculations delivered a verdict that forever changed our place in the cosmos. Andromeda was not a nearby cloud. It was a galaxy in its own right, nearly 1 million light-years away, a colossal city of stars completely separate from our own. And it was not alone. The universe was not just the Milky Way. It was a vast ocean dotted with countless galactic islands stretching out farther than anyone had ever dared to dream. But this discovery, as monumental as it was only the prelude to an even more profound revelation. As Hubble and his assistant Milton Humason measured the distances to more and more galaxies, they also analysed their light, passing it through a prism to spread it into a spectrum. And in the light from these distant island universes, they saw something strange. The distinct spectral lines of known elements like hydrogen and calcium were not where they were supposed to be. They were shifted systematically toward the red end of the spectrum. This phenomenon, known as redshift, had a stunning implication. It was the Doppler effect written in starlight. Just as the siren of a receding ambulance drops in pitch, the light from an object moving away from us is stretched, its wavelength shifting towards red. And what Hubble found was overwhelming. Almost every galaxy he could measure in every direction he looked was red shifted. They were all flying away from us. And more than that, there was a clear pattern. The fainter, more distant galaxies showed a greater redshift. The farther away a galaxy was, the faster it was receding. This was the bedrock observation, the empirical proof that Lemaitre's mathematics had predicted. The universe was not a static eternal stage. It was a single colossal explosion still unfolding before our very eyes. The priest's abominable physics was not abominable at all. It was the truth written in the ancient light of 1 million fleeing galaxies. The static universe was dead. And in its place stood a cosmos with a history, a story that began in a moment of unimaginable violence and heat. The discovery of an expanding universe opened a door into the past, a theoretical gateway back to the very first moments of time, and it was a mischievous, brilliant Russian physicist named George Gamow who dared to step through it. Gamow was a force of nature, a polymath, a prankster, and a physicist of dazzling intuition. Having fled the Soviet Union, he brought to America a uniquely bold and creative mind. While others were still grappling with the philosophical implications of the Big Bang, Gamow was already asking the next most crucial question. If you run the clock backward, If you compress the entire observable universe into a volume smaller than a marble, what are the physical conditions? The answer was obvious and overwhelming. It would be hot. Inconceivably hot. A plasma heated to billions of degrees, a cauldron of pure energy and elementary particles crushed together under impossible pressures. And in that inferno, Gamow saw not just the beginning of space and time, but the birthplace of matter itself. He saw a nuclear furnace. For centuries, scientists had believed the elements were eternal fundamental constants of nature. Then, with the dawn of the 20th century, astronomers had begun to suspect that the elements were cooked up inside the cores of stars where gravity could generate the necessary heat and pressure for nuclear fusion. Gamow proposed a third, far more audacious idea. What if the lion's share of the elements wasn't forged in stars over billions of years, but was created all at once in the first few minutes of the universe's life? It was a breathtaking leap of imagination. The Big Bang was not just the origin of expansion, it was a cosmic factory that had manufactured the building blocks of everything we see today. Working with his brilliant graduate student Ralph Alpher, and later joined by physicist Robert Herman Gamow, set out to turn this grand vision into a testable quantitative theory. Their goal was nothing less than to write the recipe for the universe. They wanted to calculate step by step how a primordial soup of elementary particles could, as the universe expanded and cooled, fuse together to form the atomic nuclei of every single element in the periodic table. They even gave a name to this primordial substance, a concept Alpha whimsically borrowed from an archaic term for primitive matter, yilm. Imagine this yilm. A fraction of a second after the beginning, it's a seething chaotic sea. Not of atoms, but of their constituent parts, protons, neutrons, electrons, photons, and other exotic particles, all crashing into each other with ferocious energy. There are no rules of chemistry here, no stable structures. It's a state of pure raw potential, a dense fog of unbound ingredients. As the universe expands, it begins to cool like a gas released from a piston. The temperature drops, and the chaos begins to subside. Gamow, Alpha, and Herman theorized that there would be a critical window of opportunity. A brief fleeting epoch lasting only a few minutes when the universe was still hot enough for nuclear reactions to occur, but cool enough for the newly formed nuclei to survive without being immediately blasted apart by high-energy photons. This was the sacred moment of creation, the genesis of the elements. Their model began with the simplest ingredients, protons and neutrons. In that early superheated plasma, these particles could begin to stick together. A proton could capture a neutron to form deuterium, the nucleus of heavy hydrogen. A deuterium nucleus could then collide with another proton, or neutron building up to form tritium or helium-3. And then two of these lighter nuclei could fuse to create the ultimate prize helium-4, a nucleus of 2 protons and 2 neutrons, a particle of exceptional stability, a true cosmic cornerstone. Alpha, a meticulous computational physicist, undertook the Herculean task of calculating the reaction rates for this entire chain. He had to model how the rapidly dropping temperature and density of the expanding universe would affect the probability of these collisions. It was a frantic race against time, a cosmic cooking show, where the oven was cooling down by the second. When he ran the numbers, the results were astounding. The theory predicted that after this brief period of primordial nucleosynthesis, the universe should be left with a very specific composition, about 75% hydrogen, the protons that never found a partner, and about 25% helium-4 by mass, with tiny trace amounts of deuterium and lithium. This wasn't just a random guess, it was a concrete falsifiable prediction. And when astronomers looked out at the oldest stars and the most pristine gas clouds in the cosmos, this is almost exactly what they found. The universe in its most ancient and unadulterated state was indeed a simple mixture of hydrogen and helium in just the proportions that Gamow's team had predicted. It was a triumph, a stunning confirmation that they were on the right path. They had seemingly deciphered the first page of the cosmic recipe book. They had explained the origin of 98% of all the atomic matter in the universe. It seemed they were on the verge of explaining everything. But as they tried to push their cosmic assembly line further to build the elements heavier than helium, they hit a wall so fundamental it seemed to be built into the very laws of nuclear physics. The problem lay with the next steps. To build a heavier element, you would need to add a proton or a neutron to a helium-4 nucleus. Adding a single particle, A proton, or a neutron to helium-4, creates a nucleus with a total mass of 5. But here nature presents a formidable obstacle. There is no stable nucleus with 5 particles. Isotopes like helium-5 or lithium-5 are so fantastically unstable that they disintegrate almost instantly in less than a trillionth of a second. They fall apart before they have any chance of capturing another particle. The cosmic assembly line would create helium, and then it would simply stop. The gateway to heavier elements was slammed shut. Perhaps they thought 2 helium-4 nuclei could fuse together directly that would create a nucleus with a mass of 8 beryllium-8. But here again, they were thwarted. Beryllium-8 is also wildly unstable, decaying back into 2 helium nuclei in the blink of an eye. It was a second impassable roadblock. The chain of creation was broken at mass 5 and broken again at mass 8. Gamo's beautiful, elegant theory had a fatal flaw. It could create a universe filled with hydrogen and helium, the fuel for future stars. But it could not forge the carbon needed for life, the oxygen. We breathe the silicon of the rocks beneath our feet, or the iron in our blood. The Big Bang, it seemed, had left its work tragically unfinished. The primeval furnace had cooled too quickly, its fire extinguished before it could create the elements necessary for a complex and interesting cosmos. The theory that had so brilliantly explained the origin of the vast majority of matter was utterly silent on the origin of the tiny, precious fraction of matter that makes our existence possible. The universe had a recipe for stars, but not for stargazers. A profound mystery now lay at the heart of creation. If the building blocks of a life were not forged in the crucible of the Big Bang, then where and how were they made? The cosmos had hidden the rest of its recipe, and a new generation of cosmic detectives would have to look elsewhere for the clues. They would have to look to the stars. And so the idea was no longer just an abstract mathematical curiosity. The concept of a beginning, a singular genesis for space and time, had moved from the realm of philosophy into the domain of physics. But a grand theory is one thing, the gritty detailed evidence is another. How could we ever hope to prove such a fantastical origin story? How could we possibly find the fingerprints of creation itself? The challenge was immense, demanding a new kind of scientific courage, a willingness to apply the known laws of the atom, the physics of the nucleus, to the entire cosmos at its very first breath. It required someone who could see the universe not just as a vast empty space dotted with galaxies, but as a unified physical system, a laboratory where the pressures and temperatures exceeded anything we could ever dream of replicating on Earth. That challenge was taken up by a team of visionary physicists in the late 1940s, led by the brilliant and irrepressibly playful George Gamow. Gamow was a titan, a polymath with a boundless imagination who saw the newborn universe as the ultimate particle accelerator. He reasoned that if the universe was expanding and cooling today, then running the clock backwards meant it must have once been unimaginably hot and dense, a primordial soup he dubbed Yilem. In this cosmic crucible, he believed, was the answer to the ancient question of where the elements came from. He recruited a sharp, meticulous graduate student, Ralph Alpha, to perform the grueling calculations needed to test this grand hypothesis. Together they set out to do the impossible to write the recipe for the universe. Their work was a breathtaking act of theoretical archaeology. They were attempting to reconstruct the first few minutes of existence, a time when the entire observable universe was smaller than a marble, a seething maelstrom of fundamental particles and pure raw energy. The conditions they modelled were almost beyond comprehension. Temperatures of billions of degrees, densities greater than that of an atomic nucleus. In this inferno there were no atoms, no molecules, no stars or galaxies. There was only a turbulent plasma of protons, neutrons, electrons, and a blinding, overwhelming flood of high-energy photons light. This sea of light was the true tyrant of the early cosmos. Its photons were like a celestial blowtorch, energetic enough to blast apart any atomic nucleus that dared to form. This was the fundamental tension Alpha and Gamow had to model, a desperate race between the constructive forces of nuclear fusion and the destructive power of the universe's own radiation. The fate of all matter hinged on a critical, fleeting window of opportunity. As the universe expanded, it cooled. The photons that formed the oppressive radiation bath began to lose their energy. There would come a moment they calculated about 1 second after the Big Bang when the temperature would drop just enough. The celestial blowtorch would be tamed. This was the moment of Genesis. At this point, a proton and a neutron could finally collide and stick together without being immediately obliterated, forming a nucleus of deuterium or heavy hydrogen. This single, fragile bond was the most important step in the entire cosmic story. It was the crucial gateway, the deuterium bottleneck. If the universe had cooled too slowly, the photons would have remained too energetic, and deuterium would never have stabilized. If it had cooled too quickly, the protons and neutrons would have lost the energy needed to overcome their mutual repulsion and fuse at all. Everything depended on getting this timing, this cooling rate, exactly right. Once deuterium could survive, a furious lightning-fast chain reaction was unleashed. The universe had just over 3 minutes to build the elements. After that, the expansion would have rendered the cosmic soup too cool and too diffuse for any further nuclear reactions to occur on a grand scale. It was a frantic 3-minute burst of cosmic alchemy. Deuterium nuclei would slam into other protons and neutrons, forming isotopes like tritium and helium-3. Then these intermediate nuclei would collide and fuse, forging the most stable and tightly bound light nucleus of all helium-4. Alpha's painstaking calculations, filling page after page with complex nuclear equations, painted a remarkably clear picture of this primordial furnace. It was brutally efficient at producing helium, but not much else. The process would effectively slam into a wall once helium-4 was formed. There are no stable nuclei with 5 or 8 particles, creating insurmountable gaps in the chain of element production. You couldn't simply add a proton or a neutron to a helium nucleus and keep going. The primordial fire, for all its intensity, was not hot or dense enough for long enough to leap over these gaps and forge heavier elements like carbon or oxygen. The Big Bang, it seemed, was not the creator of everything. It was the creator of the potential for everything. The result of their theoretical labour was published in 1948, a landmark paper that laid the foundation for our modern understanding of creation. In a characteristic stroke of wit, Gamow noticing the authors' names were alpha, and Gamow decided to add the name of his friend, the eminent nuclear physicist Hans Bethe, to the author list, even though Bethe had done no work on the paper itself. He couldn't resist the pun. The paper became famously known as the Avg Alpha Beta Gamma paper, a perfect cosmic joke for a theory about the universe's beginnings. But behind the humour was a set of stunningly precise, falsifiable predictions. The AVG paper didn't just tell a story, it made a quantitative claim. It predicted that the 3-minute fury of Big Bang nuclear synthesis would have left behind a universe composed of roughly 75% hydrogen and 25% helium by mass, with only trace amounts of deuterium and lithium. For the first time, there was a theoretical explanation for the overwhelming abundance of these two simplest elements observed in the cosmos today. It was a triumph of nuclear physics applied to the grandest possible scale. Yet buried within their calculations was an even more profound prediction, one that was almost an afterthought at the time. Alpha, along with another colleague, Robert Herman, realized something extraordinary. That ancient oppressive sea of photons, the radiation that had dictated the terms of nuclear synthesis, wouldn't simply vanish. As the universe continued to expand and cool for billions of years, this primordial light would also cool its wavelength, stretching its energy, diminishing, until it was no longer a destructive gamma ray, but a faint cold and utterly pervasive wash of microwave radiation. They calculated that this fossilized light, this afterglow of creation, should still be present today, filling every cubic centimetre of space. It would be a perfect blackbody radiator coming at us from every direction, with a temperature just a few degrees above absolute zero. They predicted a temperature of around 5 Kelvin. Here was the ultimate proof, a genuine smoking gun. If they were right, the echo of the Big Bang was not just a metaphor. It was a physical reality, a whisper from the dawn of time waiting to be detected. But the world of physics was not yet ready for such a revelation. The AVG paper was brilliant, but it was also far ahead of its time. The scientific community largely ignored it. The competing steady-state theory, which proposed a universe that was eternal and unchanging, was gaining traction, and seemed to many more elegant. Alpha and Hermann's incredible prediction of a cosmic afterglow faded into obscurity, a footnote in the history of a bold but unproven idea. For nearly 2 decades, the universe kept its greatest secret. The evidence for our own fiery birth was all around us, streaming past us and through us every single second, but we simply didn't have the eyes to see it. The question of our origins remained locked in a stalemate between 2 grand theories, a cosmic mystery that seemed destined to remain unsolved. The solution, when it came, would not be found by cosmologists searching for the secrets of the universe. It would be found by 2 engineers trying to get rid of some annoying static. The year is 1964. We are at Bell Telephone Laboratories in Holmdel, New Jersey. 2 radio astronomers, Arno Penzias and Robert Wilson, are working with a magnificent and peculiar instrument, the Holmdel Horn antenna. It was a giant gleaming structure originally built to communicate with the first generation of orbital satellites like Echo 1. But with satellite technology advancing rapidly, the horn was now obsolete. Penzias and Wilson were repurposing it for a new task to make precise measurements of radio waves coming from the Milky Way. To do this, their antenna had to be perfect. Their work required absolute precision, which meant systematically identifying and eliminating every possible source of background noise. They were in essence trying to create perfect silence. They calibrated their instruments, chilled their receiver with liquid helium to just a few degrees above absolute zero to minimize its own thermal noise, and began to listen to the cosmos. Almost immediately they hit a snag. A stubborn, persistent and deeply irritating hiss. It was a faint, low-level microwave signal that simply would not go away. It was a tiny anomaly, a whisper of energy equivalent to a temperature of just 3.5 Kelvin, but in a field where precision is everything, it was an infuriating imperfection. The noise was most frustratingly isotropic. It was the same everywhere. No matter where they pointed the giant horn in the sky, the hiss remained. It was the same day and night, summer and winter. This was bizarre. If the noise were coming from our sun, it would vanish at night. If it were coming from the centre of the Milky Way, it would grow stronger and weaker as the Earth rotated. But this signal was constant, a monotonous hum underlying the entire cosmos. Penzias and Wilson were methodical engineers, not speculative theorists. They assumed the fault was with their equipment or their environment. They spent months embarking on a cosmic wild goose chase. They checked and rechecked every wire, every switch, every amplifier. They pointed the antenna directly at New York City to see if urban radio interference was the culprit, but found nothing. They considered atmospheric noise, but the signal didn't change with altitude or weather. They even began to worry about more exotic possibilities, like radioactive fallout from high-altitude military tests. Nothing fit the data. Their most famous and perhaps most desperate attempt at a solution involved a pair of pigeons that had taken up residence inside the giant horn. Penzias and Wilson theorized that the birds' droppings, what they politely termed a white dielectric material, might be warming up and emitting microwaves that were interfering with their measurements. They climbed into the antenna, captured the pigeons, and meticulously cleaned out the entire structure. The pigeons were mailed 60 miles away, only to promptly fly back. After their second removal, more permanent measures were taken. They powered up the antenna again, praying for that perfect clean silence. The hiss was still there, unchanged, unyielding, unexplained. They were at a complete loss. This unwanted noise, this ghost in their machine, had resisted every rational explanation. It seemed to be an intrinsic property of the sky itself. It was as if the empty space between the stars was not actually cold and dark, but was instead faintly glowing with a uniform microwave warmth. In a moment of frustration, Penzias was on the phone with a colleague at another university mentioning their bizarre problem. His friend suggested he call a group of physicists just a few miles down the road at Princeton University. A team there, led by a researcher named Robert Dickey, was apparently interested in finding faint microwave signals from outer space. The call Penzias made that day would change the course of human history. At Princeton, Dick and his team, including a young Jim Peebles, had independently retraced the theoretical steps of Gamo and Alpha. Unaware of that earlier forgotten work, they had reasoned that if the universe had begun in a hot, dense state, it must be filled with a remnant afterglow. They had come to the same stunning conclusion: a cosmic microwave background should exist with a temperature of a few Kelvin. In fact, At the very moment Penzias was struggling with his pigeon problem, the Princeton team was busy building their own specialized radiometer to go hunting for this very signal. They were building a detector to find the echo of creation. And then the phone rang. When Penzias described the persistent isotropic hiss, its unexplainable nature, and most importantly its measured temperature of about 3 Kelvin, a wave of understanding washed over the room in Princeton. The story goes that after he hung up the phone, Robert Dickey turned to his crestfallen colleagues and said, "Boys, we've been scooped." They knew instantly what Penzias and Wilson had found. It was not equipment malfunction, it was not pigeon droppings, it was not radio interference from New York City. The annoying static that had plagued the Bell Labs engineers for months was the sound of the birth of the universe. It was the fossil light from the primordial fireball, the very afterglow predicted by Alpha and Herman 16 years earlier. It was the most important discovery in the history of cosmology, and it had been found entirely by accident. The discovery of the cosmic microwave background, or CMB, was the final irrefutable piece of evidence. It was the observational proof that our universe had indeed begun in a state of unimaginable heat and density. The steady-state theory, elegant as it was, could offer no plausible explanation for this uniform thermal glow filling all of space. It died almost overnight. The Big Bang was no longer just a theory, it was a measured reality. The discovery transformed our understanding of our own cosmic story. For Ralph Alpha, it was a moment of profound, if bittersweet, vindication. The prediction he had made as a graduate student, the idea that had been ignored for so long, was now confirmed with astonishing precision. His cosmic recipe, cooked up with pencil and paper, had described the real universe. The 25% helium we see in the oldest stars was not an accident. It was the leftover ash from the Big Bang's furnace, and the CMB was the residual heat from that very same fire. The 2 lines of inquiry, the audacious theoretical prediction of the Avicii paper, and the painstaking accidental observation at Bell Labs, had converged in one of the most beautiful moments in the history of science. The whisper Penzias and Wilson detected was the proof that the furnace Alpha and Gamma had imagined was real. We now knew with a certainty that was once unimaginable that our universe had a birthday. We knew the conditions of that first violent moment. We had found the echo of creation, a sound that had been travelling across the cosmos for 13.8 billion years, waiting for someone to finally listen. We had deciphered the first chapter of the universe's autobiography, a story of fire and fusion written in a language of hydrogen and helium. But this triumphant discovery also brought new, more difficult questions into focus. The Big Bang had forged the starting materials, yes, but looking around us we see a universe filled with complexity. We see carbon-oxygen ion, the elements of planets of life. If the primordial furnace slammed shut after just a few minutes, if it could only create the lightest elements, then where did everything else, everything that truly matters to us, come from? The cosmic stage was set, the raw materials were in place, but another act in the grand drama of creation was about to begin. And so the symphony of creation reaches its first great crescendo. The quark-gluon plasma, that unimaginably hot and dense state where the very concept of individual particles was meaningless, has vanished forever into the history of a cooling cosmos. We have crossed the threshold of the first microsecond. In this fleeting moment, the universe has expanded and cooled just enough for the strong nuclear force, the most powerful of nature's architects, to finally seize control. It reaches into the roiling sea of energy and pulls together the fundamental quarks, binding them in unbreakable trios. For the first time, matter as we know it begins to emerge. Protons forged from 2 up quarks and 1 down, and their neutral siblings neutrons built from 2 down quarks and 1 up, flood the infant cosmos. They are the raw timber, the foundational bricks from which every star, every planet, and every living thing will one day be constructed. But they are not yet permanent. The universe is still a cauldron of furious energy, a place where particles are not fixed identities, but transient states, in a constant violent dance of transformation. The temperature hovers around 10 trillion degrees, a heat so intense that it fuels a relentless cycle of change. A proton can absorb a high-energy electron and through the subtle intervention of the weak nuclear force transform its very nature, shedding its charge to become a neutron. A moment later that same neutron might collide with a positron, or simply decay, flipping a quark and re-emerging as a proton. Back and forth, they flicker a billion times a second, protons becoming neutrons and neutrons becoming protons. Their existence is a precarious balance, a cosmic equilibrium dictated by the raw energy of their surroundings. In this maelstrom, for every 7 protons that materialized from the quark chaos, there was roughly 1 neutron. This ratio 7:1 seems like a simple cosmic footnote, but it is perhaps the single most important number in the history of the universe. It was etched into the fabric of reality at this precise instant, a decision from which there would be no appeal. This number will dictate the amount of helium the Big Bang can produce, which in turn will govern the lifetime of the first stars, the evolution of galaxies, and the ultimate chemical destiny of everything that will ever be. The stage is now set. The actors are present. We have a universe filled with a thick, searingly hot fog of protons, neutrons, electrons, and a blinding storm of light in the form of high-energy photons. The force that built these particles, the strong force, is eager to continue its work to bind protons and neutrons together into the first atomic nuclei. The cosmic clock is ticking loudly. The inexorable expansion of space-time is driving the temperature down with terrifying speed. With every passing moment, the universe becomes cooler, less dense, the particles moving farther and farther apart. This process of creation is a race against the encroaching cold and darkness. If the strong force is to build the elements, it must do so now, while the cosmos is still a nuclear furnace. The first most logical step in this celestial construction project seems simple enough: fuse 1 proton and 1 neutron. This combination would create a nucleus of deuterium, also known as heavy hydrogen. It is the essential gateway, the first rung on the ladder leading to all the heavier elements. Without stable deuterium, the entire enterprise of nucleosynthesis is doomed before it can even begin. And here, in the first second of existence, the universe encounters a devastating obstacle. A barrier so profound it brings the engine of creation to a grinding, screeching halt. We call it the deuterium bottleneck. Imagine trying to build the most delicate structure imaginable in the heart of a thermonuclear explosion. That is the challenge facing the early universe. A proton and a neutron do in fact find each other. Pulled together by the irresistible grip of the strong force, they collide and merge, releasing a pulse of energy as they settle into a more stable combined state. For an infinitesimal fraction of a second, a deuterium nucleus is born. A new form of matter exists. Creation has taken its next step. But this fledgling nucleus is tragically fragile. The energy that binds it together, its binding energy, is remarkably low, a mere whisper of force compared to the titanic energies still raging around it. And the universe at this moment is saturated with photons, particles of light, but they are not the gentle photons of a sunny day. They are gamma rays of unimaginable power, each one a celestial hammer carrying far more energy than is required to shatter the delicate bond holding the deuterium nucleus together. So the moment a deuterium nucleus forms, it is annihilated. A gamma-ray photon, one of billions, screaming through every cubic centimetre of space, slams into the newborn nucleus. The impact is catastrophic. The fragile bond is instantly broken, and the proton and neutron are blasted apart, flung back into the primordial soup, as if their brief union had never happened. For thousands upon thousands of these fleeting attempts, the outcome is the same. A proton and a neutron meet. They fuse. A photon destroys them. Creation takes one step forward and is immediately thrown one step back. It is a cosmic exercise in futility. The universe is hot enough to want to build, but it is too hot to let anything that it builds survive. This is the bottleneck. All of cosmic alchemy is stalled, held hostage by the very heat that makes fusion possible. No deuterium means no helium means no heavier elements. The path forward is completely blocked. If the universe were to remain this hot forever, it would be a profoundly boring place, an eternal, undifferentiated soup of protons and electrons, a failed creation. But the universe has a saviour, its own expansion. The clock continues to tick. Second after agonizing second passes. The cosmos continues to swell, to stretch, to thin out. And with every moment of expansion, the temperature drops. The photon storm, once a raging, all-destroying hurricane, begins to lose its fury. The photons, stretched to longer wavelengths by the expansion of space itself, are steadily losing their destructive energy. The celestial hammers are becoming softer. 1 second ticks by. 10 seconds. A minute. The temperature once measured in the trillions of degrees plummets to a mere billion. It is still fantastically hotter than the core of any star that will ever exist, but for the universe, this represents a critical life-giving cooldown. And then, somewhere around the 2-minute mark, we reach the tipping point, the magic threshold. The average energy of the photons finally drops below the binding energy of deuterium. The hurricane has subsided into a gale. The celestial hammers can no longer shatter what the strong force builds. Suddenly, when a proton and a neutron fuse, the resulting nucleus survives. It holds together. The bottleneck is broken. The dam has burst. What happens next is one of the most violent and efficient acts of creation in the history of the universe. It is a frantic 20-minute period of unrestrained nuclear fusion that will determine the chemical composition of primordial gas for billions of years to come. With the gateway now open, deuterium nuclei begin to accumulate, no longer being instantly destroyed. They become the crucial building blocks for the next stage of cosmic architecture. The universe, having been thwarted for minutes now, works with astonishing speed, as if it knows its time is limited. A newly formed deuterium nucleus, a proton and a neutron bound together, immediately finds itself in a target-rich environment. It might collide with another proton. The strong force takes over, fusing them into a new, more complex nucleus, with 2 protons and 1 neutron. This is helium-3. A flash of gamma radiation is released, carrying away the excess energy. A stable isotope of a new element has been born, or that deuterium nucleus might collide with another neutron. Again, they fuse, creating a nucleus with 1 proton and 2 neutrons. This entity is called tritium, a heavy and unstable isotope of hydrogen. It is another stepping stone on the path to something greater. In the cosmic crush of this primordial furnace, another possibility unfolds with startling frequency. A deuterium nucleus collides with another deuterium nucleus. This fusion can proceed down 2 different pathways, both producing a new element while ejecting a spare nucleon. One path yields a helium-3 nucleus and a free neutron. The other results in a tritium nucleus and a free proton. In every direction we look, the result is the same. The simple nuclei of deuterium are being rapidly and irreversibly consumed, converted into the more complex, more stable nuclei of helium-3 and tritium. The universe is climbing the ladder of complexity 2 rungs at a time, but helium-3 and tritium are not the final destination. They are merely the final intermediaries in this breathtaking sequence of creation. They are themselves consumed almost as quickly as they are made. A nucleus of helium-3 containing 2 protons and 1 neutron now collides with a free-roaming neutron from the soup. The resulting fusion is the grand prize of this entire process. The particles merge to form a nucleus with 2 protons and 2 neutrons. This is helium-4. It is one of the most perfect, most stable configurations in all of nuclear physics. Its binding energy is immense, a deep gravitational well from which its constituent particles will never escape. When it forms, it releases a tremendous burst of energy, sealing its own structure and becoming a permanent fixture of the cosmos. Simultaneously, a nucleus of tritium with its 1 proton and 2 neutrons collides with a free proton. The outcome is identical. The fusion creates that same, supremely stable configuration of 2 protons and 2 neutrons. Another helium-4 nucleus is born, locking away its components forever. This is the primary production line of the infant universe. A cascade of reactions, all starting with the fusion of a proton and a neutron flowing through the ephemeral channels of deuterium, helium-3 and tritium, and terminating overwhelmingly in the stable final form of helium-4. It is a production line of stunning efficiency. Remember that 7-to-1 ratio of protons to neutrons, frozen into the universe in the first second. Now we see its ultimate consequence. The neutrons are the limiting ingredient in this cosmic recipe. Every available neutron is desperately seeking a proton to begin the nucleosynthesis chain. Because helium-4 requires 2 protons and 2 neutrons, it is the most efficient way for the universe to bind up all the available neutrons into stable nuclei before they have a chance to decay. And that is precisely what happens. Within about 3 minutes of the bottleneck breaking, nearly every single free neutron in the entire universe has been captured. They are pulled out of the cosmic soup and permanently locked away inside the unbreachable fortress of a helium-4 nucleus. When the dust settles from this flurry of creation, the result is a universe whose fundamental composition has been set. Out of the original matter, about 75% remains as individual protons, the nuclei of ordinary hydrogen. They are the lonely survivors, the particles that never found a neutron partner during the brief window of fusion. Almost all of the remaining 25% of the universe's normal matter has been converted into helium-4. For every 12 hydrogen nuclei, there is now one nucleus of helium. This prediction, a universe that is 3/4 hydrogen and 1/4 helium by mass, is one of the most powerful and successful pillars of the Big Bang theory. When we point our telescopes to the most ancient pristine gas clouds in the distant universe, this is exactly the ratio we find. We are in effect seeing the direct chemical fingerprint of those first few minutes of creation, but the process wasn't perfectly 100% efficient. A tiny fraction of the intermediate products managed to survive the frantic fusion era. A few nuclei of deuterium, perhaps one in every 100,000, failed to find another particle to fuse with before the universe expanded and cooled too much. They remain today as a precious relic, a cosmic fossil, whose abundance tells us with exquisite precision just how dense the universe was during this epoch. An even smaller amount of helium-3 also survived the gauntlet. But what about heavier elements? Could this process continue building on helium-4 to forge things like carbon and oxygen? The universe certainly tried. A helium-4 nucleus might collide with a tritium nucleus, fusing to form a nucleus with 3 protons and 4 neutrons. This is lithium-7, a stable element. Or a helium-4 nucleus could collide with a helium-3 nucleus, creating beryllium-7, which would later capture an electron and decay into that same stable lithium-7. These reactions did happen. They produced the universe's first smattering of a third element. But the quantities are almost immeasurably small. For every 10 billion hydrogen atoms, there is only 1 atom of lithium forged in the Big Bang. Why? Because here the universe ran into its next great wall. There is no stable nucleus with 5 particles and no stable nucleus with 8 particles. Trying to add a proton or a neutron to a helium-4 nucleus results in an entity that disintegrates almost instantly. Trying to fuse 2 helium-4 nuclei together results in a beryllium-8 nucleus, which is so unstable it decays back into 2 helium-4 nuclei in less than a trillionth of a second. The ladder of creation had a missing rung. The path to carbon and all the heavier elements was blocked by an insurmountable barrier of nuclear physics, and at the same time the clock was running out. By the time 20 minutes have passed since the beginning, the universe has become a ghost of its former self. The temperature has dropped below what is needed to overcome the electrical repulsion between nuclei. The density has fallen so far that collisions once constant and unavoidable have become rare, improbable events. The great cosmic furnace has cooled. The window of opportunity open for just a brief glorious quarter of an hour has slammed shut. Nucleosynthesis is over. The frantic universe-spanning fire of creation has been extinguished, leaving behind a cosmos of vast, simple and profound purity. A universe made of hydrogen, helium, and a trace of lithium and nothing more. The raw materials for stars have been forged, but the elements of life of planets of you are nowhere to be found. For those, a new kind of furnace would be needed, a furnace inside the heart of a star. And the universe would have to wait hundreds of millions of years in the cold and the dark before the first of those would finally ignite. And so the frantic furnace of the first 3 minutes cools. The universe, having passed through its incandescent baptism, settles into a new, quieter state of being. In that fleeting, violent overture, a cosmic recipe was written, a foundational formula that would dictate the destiny of everything to come. What emerged from that primordial forge was not a universe teeming with variety, but one of astonishing stark simplicity. Across the entire expanse of space-time, the elemental ledger was now set. For every 10 hydrogen nuclei, the simplest element of all, there was roughly 1 nucleus of helium. By mass, this meant the cosmos was now a vast transparent ocean of about 75% hydrogen and nearly 25% helium. It was a stunning victory for theory, a prediction so precise and so magnificently confirmed by observations of the oldest, most pristine corners of the cosmos, that it stands as one of the great pillars of our modern understanding. Imagine you're looking out across this newborn universe. There are no stars to pierce the darkness, yet no galaxies spiraling in silent majesty. There is only gas, an endless, featureless and utterly uniform sea of hydrogen and helium, punctuated by the faintest trace amounts of deuterium, helium-3 and lithium. This is the inheritance of the Big Bang. This primordial composition is not some abstract calculation. It is a physical reality that we can touch with our telescopes. When we peer into the distant past using the light from ancient quasars as cosmic flashlights, we can see how that light is absorbed by the virgin gas clouds it passes through. In the spectral fingerprints of these clouds that have remained virtually untouched for over 13 billion years, we find the echo of the Big Bang's first minutes. We see the predicted ratio of hydrogen to helium time and time again, a universal constant written into the very fabric of existence. It is the universe's birth certificate, and the signature is unmistakable. This profound uniformity tells us something remarkable, that every part of the observable cosmos we see today, from the Andromeda Galaxy to the most distant clusters, all began from the same common stock. We all share the same elemental ancestry forged in the same initial crucible. It is the single greatest piece of evidence for a shared beginning, a moment when everything was one. But this elegant simplicity, this triumphant confirmation of our models, conceals a profound and startling challenge. The very efficiency and speed of Big Bang nuclear synthesis, the source of its predictive power, was also its greatest limitation. The process was brutally, unforgivingly brief. The window of opportunity, that perfect Goldilocks moment when the universe was hot and dense enough for fusion, but cool enough for nuclei to hold together, lasted for only about 17 minutes. After that, the universe had expanded and cooled so much that the particles were too far apart and moving too slowly to overcome their mutual electrical repulsion. The forges went cold. The era of cosmic fusion was over, seemingly for good. And in its haste, the Big Bang had left a critical gaping hole in its own creation. It had successfully built the foundation, laying down vast quantities of hydrogen and helium, but it had failed to construct the next floor. The universe was left with a debilitating problem, a cosmic chasm on the periodic table that it had no immediate way to cross. To understand this gap, we have to think like cosmic engineers trying to build heavier elements. The logical next step after creating helium-4, which has 2 protons and 2 neutrons, would be to add another proton or another neutron. Adding a neutron to a helium-4 nucleus creates helium-5. Adding a proton creates lithium-5. Here is the crux of the problem: both helium-5 and lithium-5 are catastrophically unstable. They disintegrate almost instantaneously in less than a trillionth of a second. They are not viable building blocks. They are fleeting phantoms that vanish the moment they appear. Nature, it seemed, had locked the door on this path to heavier elements, so the early universe tried a different approach. What if you could fuse 2 helium-4 nuclei together? 2 plus 2 makes 4 protons, and 2 plus 2 makes 4 neutrons. This combination creates a nucleus of beryllium-8. For a tantalizing moment, it seems like a bridge has been found. Beryllium-8 could in theory capture another helium-4 nucleus to finally leapfrog the instability and form the stable essential nucleus of carbon-12. Carbon, the very backbone of life, consists of 6 protons and 6 neutrons. The pathway seemed clear: helium plus helium makes beryllium, and beryllium plus helium makes carbon. But the universe is rarely so straightforward. Beryllium-8, this crucial stepping stone, is itself spectacularly fragile. Its existence is so ephemeral, it makes the fleeting lives of helium-5 and lithium-5 seem like eternities. Beryllium-8 decays back into 2 separate helium nuclei in just under 1/10 quadrillionth of a second. It is an impossible crumbling bridge. For carbon to be made, a 3rd helium nucleus would have to strike this beryllium-8 nucleus during its impossibly short lifespan. In the conditions of the early universe, this was a statistical impossibility. The cosmos was expanding far too rapidly. The density of particles was plummeting with every passing microsecond. By the time there was a significant amount of helium available to attempt this 3-body collision, the universe was already too dilute and too cool. The chances of 3 helium nuclei finding each other in the right place at the right time to perform this delicate 3-step dance before the beryllium-8 bridge collapsed were effectively 0. It was like trying to assemble a complex watch in the middle of a titanic explosion. The parts were there, but the environment was too chaotic and changing too fast. The result was an elemental dead end. The Big Bang created the fuel for future stars, but it could not create the carbon for future life, the oxygen for future water, or the silicon for future planets. The universe was left chemically impoverished, a vast expanse of simple gas, beautiful in its purity, but sterile and without potential for complex structure. This is not a flaw in the theory. On the contrary, it is one of its most vital and illuminating predictions. The theory of Big Bang nucleosynthesis doesn't just tell us what the universe did make, it also tells us what it could not make. And this limitation, this predicted gap in the elemental chain, is precisely what we observe. The oldest stars, the purest relics of the early cosmos, are almost entirely devoid of elements heavier than helium. Their chemical composition is a perfect match for the simple recipe cooked up in the first few minutes. This absence is not a mystery, it is a confirmation. It tells us that the rich tapestry of elements that makes our world possible, the carbon in our bodies, the iron in our blood, the gold in our vaults, must have come from somewhere else. Another creative force was needed. The Big Bang had set the stage, but a new cast of characters would be required to perform the rest of the cosmic play. It had written the first chapter, but the story of creation was far from over. Yet even within this grand success, within this framework of triumphantly confirmed predictions, there lurks a subtle but persistent ghost. It is a tiny crack in the otherwise perfect edifice of the theory, a nagging discrepancy that has puzzled cosmologists and nuclear physicists for decades. It is a detective story on a cosmic scale known simply as the lithium problem. The theory of Big Bang nucleosynthesis, using the precise measurements of the universe's early conditions from the cosmic microwave background, doesn't just make a general prediction for the light elements, it makes exquisitely specific ones. It predicts the amount of deuterium, helium-3, helium-4, and one specific isotope of lithium, lithium-7 with stunning mathematical certainty. The predictions for deuterium and helium are spot on. They match our observations of the primordial universe with breathtaking accuracy. But lithium is the odd one out. The theory predicts that a certain very specific amount of lithium-7 should have been forged in the Big Bang. When we go out and measure the amount of lithium in the oldest, most primitive stars in our galaxy's halo stars that act as pristine time capsules, preserving the cosmic recipe from 13 billion years ago, we find a number. And that number is wrong. Or rather, it is stubbornly, consistently, and inexplicably different from the prediction. The amount of lithium we see is about a third of what our best, most refined models of the Big Bang say should be there. It's not a huge error. We're not off by orders of magnitude. But in a field where precision is everything, a factor of 3 discrepancy is a chasm. It's like following a perfect recipe for a cake, measuring every ingredient to the gram, and somehow ending up with only a third of a cake. Something somewhere is not right. This lithium problem has become one of the most significant unsolved puzzles in modern cosmology. Scientists, like determined detectives, have pursued 2 main lines of inquiry. The first possibility is that our understanding of stars is incomplete. Perhaps these ancient stars, over their immensely long lifetimes, have somehow destroyed the lithium that was originally in them. We know that lithium is a fragile element easily burned up in the hot interiors of stars. The surfaces of these old stars are convective, like a boiling pot of water, so maybe the surface material where we measure the lithium gets dredged down into the hotter core and obliterated over billions of years. This is the astrophysical solution. Countless models of stellar evolution have been developed to try and account for this missing lithium. They incorporate rotation, magnetic fields, turbulent mixing, and a host of other complex physical processes to see if they can force the star to destroy just the right amount of lithium-7, while leaving all the other primordial elements untouched. But so far, no model has been able to do it convincingly without looking forced or unnatural. It seems difficult to hide 2/3 of the universe's original lithium inside stars without leaving other telltale signs. This leads us to the second and far more tantalizing line of inquiry. What if the problem isn't with the stars? What if the problem lies with our understanding of the Big Bang itself? What if the standard model of cosmology, as successful as it is missing a piece? This is the cosmological solution, and it opens a doorway to new and exotic physics. Perhaps there were other undiscovered particles present in the primordial furnace. Maybe hypothetical particles predicted by theories like supersymmetry existed in the hot plasma of the early universe. These particles, as they decayed, could have interacted with the existing nuclei, potentially destroying the newly formed lithium-7, or altering the nuclear reaction rates in just the right way to suppress its production. For example, the decay of a massive unstable particle could produce high-energy neutrons that would then collide with and shatter the fragile lithium nuclei. This would be a profound discovery. The missing lithium would cease to be a problem and would instead become the first concrete evidence for physics beyond the standard model of particle physics, our current best theory of fundamental forces and particles. The discrepancy would be a clue, a fossil left over from the Big Bang that points the way to a deeper, more complete understanding of reality. Scientists are attacking this problem from all angles. Astronomers use the world's most powerful telescopes like the Keck Observatory and the Very Large Telescope to hunt for even older and more chemically pristine stars, pushing our observational frontier back closer to the beginning of time to get the purest possible sample of the cosmic mixture. They search for any star that might have retained its full original lithium budget, a Rosetta star that could resolve the issue. Meanwhile, nuclear physicists in laboratories on Earth are working to remeasure the crucial nuclear reactions that govern the production of lithium. They smash beams of particles together in accelerators, meticulously recreating the energies of the early universe to refine our knowledge of exactly how these nuclei interact. A tiny, previously unaccounted for subtlety in one of these reaction rates could potentially resolve the entire discrepancy. Every possibility must be checked, every stone unturned. This persistent lithium problem beautifully illustrates the nature of science itself. It is not a failure of the Big Bang theory. On the contrary, the theory is so successful, so precise, that a small anomaly like this stands out in sharp relief. It is a testament to the model's power that we can even identify such a subtle issue. This is how science progresses. It pushes forward until it finds a crack, a small inconsistency that doesn't fit. Then it focuses all its attention on that crack because that is where the light of a new discovery is most likely to shine through. Whether the solution lies in the complex lives of ancient stars or in the realm of undiscovered particles, the quest to solve the lithium problem is pushing the boundaries of our knowledge, forcing us to refine our theories of both the very large and the very small. The simplest elements are, it turns out, posing some of the deepest questions, and so we find our universe at a pivotal moment. The first act of creation has concluded, leaving behind a cosmos of stark and simple beauty. It is a universe of potential filled with the raw fuel, hydrogen and helium that will power the future. But it is a universe in waiting. It is a dark, silent place lacking the heavier elements required to build anything solid, anything complex, anything alive. The great cosmic forge of the Big Bang has gone cold, and its elemental bridge to complexity lies in ruins. For the next chapter of the cosmic story to begin, for the universe to awaken from its simple gaseous slumber, a new kind of furnace would be needed. The cosmos required countless new crucibles scattered throughout the darkness that could succeed where the Big Bang had failed. It needed to gather its primordial gas into fiery, dense cores, reigniting the fires of fusion. The universe needed to invent stars. And so the theory stood a monument of calculation and logic, a complete self-contained story of the universe's first moments. It was a breathtaking intellectual achievement predicting the precise chemical composition of a newborn cosmos from the fundamental laws of physics. Yet for all its elegance, it remained just that, a theory, a ghost story whispered in the language of mathematics. Without proof, without tangible evidence drawn from the universe itself, it was nothing more than a brilliant speculation. The cosmos, vast and silent, held the final verdict. The challenge laid before us was monumental, a task of cosmic forensics on an unimaginable scale. How could we possibly test a prediction about the first 3 minutes when 13.8 billion years of cosmic evolution stood between us and that fiery dawn? The universe we inhabit today is a place of profound contamination. Over eons, countless generations of stars have lived and died, great nuclear forges transmuting the pristine, simple gas of the Big Bang into a rich tapestry of heavier elements. The carbon in your cells, the oxygen you breathe, the iron in your blood, all are the products of this later stellar alchemy. To find evidence for Big Bang nucleosynthesis, we needed to find a time capsule. We had to locate pockets of the universe that had somehow escaped this relentless cycle of enrichment regions that were for all intents and purposes fossilized remnants of that primordial era. We needed to become cosmic archaeologists searching not for buried cities, but for the universe's most ancient and unblemished gas. The search began not by looking for what was there, but by looking for what was absent. Our target was matter, with the lowest possible metallicity, an astronomical term of art where anything heavier than hydrogen and helium is simply called a metal. A low metal environment is a sign of purity, an indicator that the gas has not been significantly processed through stars. Our telescopes, the great eyes of humanity, began to peer into the dimmest, most distant corners of existence. We turned our gaze towards small, faint, irregular galaxies, cosmic backwaters, where star formation has been slow and inefficient. Within these unassuming galaxies lie vast glowing clouds of hydrogen gas, energized by the fierce ultraviolet radiation of a few young massive stars. These clouds, known as HI regions, are the perfect laboratories. As the hydrogen gas glows, its light can be captured and split into a spectrum, a rainbow of constituent frequencies. Embedded within this rainbow are sharp, dark and bright lines, the unambiguous fingerprints of the elements present. Each element absorbs and emits light at its own unique characteristic set of frequencies. By meticulously analysing the intensity of these spectral lines, we can deduce with astonishing precision the chemical abundance of the cloud. It is a technique of immense power, allowing us to perform a chemical assay on a gas cloud millions of light years away. For decades, astronomers painstakingly gathered spectra from these metal-poor galaxies, each one a tiny piece of a grand puzzle. They plotted their results on a graph measuring the abundance of helium against the abundance of heavier elements like oxygen. As they looked at galaxies with less and less oxygen, that is, galaxies that were more and more primordial, a stunning pattern emerged. The amount of helium was not dropping to zero. Instead, it was leveling off at a distinct immovable floor. No matter how pristine the environment, no matter how far back in time they looked, they could not find any place in the universe with less than about 24 to 25% helium by mass. A quarter of all the normal matter forged in the Big Bang was helium. This was it. The first great observational pillar of the theory. The number predicted on paper, born from the physics of a hot dense particle soup, was etched into the very fabric of the cosmos. It was a universal constant, a relic number from the beginning of time, and we had found it. This discovery was a profound vindication, but the scientific soul is rarely satisfied with a single piece of evidence. The case needed to be airtight. The true crucible for the theory, the most demanding and sensitive test of all, lay with a far more elusive element, deuterium. Deuterium, that heavy isotope of hydrogen with one proton and one neutron, is the universe's most fragile nucleus. It is an intermediate step in the primary fusion chain that powers stars like our Sun. Within the ferocious heart of a star, deuterium is created one moment and almost instantly consumed the next, fused into helium. Stars therefore are net destroyers of deuterium. They never create it and release it back into the cosmos. This unique fragility makes deuterium an extraordinary cosmic barometer. Any deuterium we measure today in a pristine environment can only be the deuterium that was created during that brief window in the Big Bang. Its abundance has only ever gone down. Measuring its primordial level would therefore provide an incredibly sensitive check on the conditions of the early universe, especially the density of ordinary matter. The problem deuterium is exceptionally rare. The Big Bang only produced about one deuterium nucleus for every 100,000 hydrogen nuclei, and its spectral signature is agonizingly subtle, a tiny, almost imperceptible shift from the overwhelmingly bright signal of ordinary hydrogen. It was like trying to hear a single pin drop in the middle of a hurricane. The metal-poor galaxies nearby were simply not pristine enough. Their starlight would have destroyed some of the local deuterium, muddying the waters. To find a true sample, we had to perform an act of observational audacity that sounds like science fiction. We had to look for something that was for all practical purposes completely invisible. We needed to find ancient clouds of primordial gas floating in the utter blackness of intergalactic space, untouched for billions of years. But how do you observe a cloud that isn't glowing? The answer was ingenious. You find a backlight. You find the brightest objects in the entire universe, distant quasars, the blazing hearts of galaxies powered by supermassive black holes, and you use their light as a cosmic flashlight. Imagine this. The light from a quasar begins a journey across the universe to us, a journey that can take 10-12 billion years. Along that immense path, it happens to pass through one of these invisible ancient clouds of hydrogen and deuterium gas. As the brilliant continuous spectrum of light from the quasar passes through the cloud, the atoms within the cloud absorb tiny specific frequencies of that light. The hydrogen atoms pluck out their characteristic frequencies, and the exceedingly rare deuterium atoms pluck out theirs. When that light finally arrives at our telescopes on Earth, its spectrum is no longer continuous. It is riddled with dark, narrow absorption lines, a cosmic barcode that tells us with breathtaking precision exactly what was in that otherwise invisible cloud billions of years ago. This technique is the pinnacle of observational cosmology. The series of absorption lines from countless clouds along the line of sight is poetically known as the Lyman Alpha Forest, a thicket of spectral data that maps the cosmic web. Somewhere within that dense forest of hydrogen lines, astronomers had to find the impossibly faint line of deuterium. It demanded the largest telescopes on Earth pointed at a single quasar for hours, even nights on end, patiently gathering every last photon from the edge of the visible universe. It required computers to model the complex physics of the gas cloud and disentangle the minuscule deuterium signal from the cacophony of surrounding noise. It was and is one of the most technically demanding measurements in all of science. Teams of astronomers around the world working independently embarked on this quest. They found their distant quasars. They identified the perfect simple absorption systems, a single clean cloud along the line of sight. They spent years refining their techniques. The tension was immense. The Big Bang theory, through its connection to another great pillar of cosmology, the cosmic microwave background radiation, made an exquisitely precise prediction for the primordial deuterium abundance. It was a single specific number. If the quasar observations found a different number, the entire elegant edifice of our cosmic understanding could develop a serious crack. Then, the results came in. One by one, the teams published their findings. From different quasars in different directions of the sky, looking through clouds, separated by billions of years of cosmic history, they all found the same thing. The measurements converged on a single value. And that value was in breathtaking, stunning, almost perfect agreement with the prediction. It was an unparalleled triumph. The deuterium abundance, the most sensitive probe of the Big Bang's conditions, matched the theory. It was like predicting the exact concentration of a single type of pollen in a sealed room from 10,000 years ago, and then finding a sample of that ancient air and confirming the prediction down to the last decimal point. This concordance between the theory of the first minutes and the observation of the universe billions of years later was a scientific masterstroke. We had used two completely different sets of physics, the nuclear physics of the hot Big Bang and the atomic physics of light absorption in a cold gas cloud, and two completely different sets of observations, the faint afterglow of the Big Bang and the light from distant quasars, to measure a fundamental property of our universe. And they gave the same answer. This wasn't just a confirmation, it was a powerful synthesis, a unification of our cosmic story. The same parameter, the baryon density of the universe that explained the pattern of fluctuations in the cosmic microwave background, also perfectly predicted the amount of deuterium and helium forged in the primordial furnace. It was a symphony of evidence with every instrument playing in perfect harmony. Of course, no story in science is ever truly complete. The other two light elements, helium-3 and lithium, also have predictions. Helium-3 is notoriously difficult to measure primordially, but the few observations we have are broadly consistent with the theory. Lithium, however, remains a persistent, tantalizing puzzle. When we look at the oldest, most metal-poor stars in our own galaxy, stars that should be time capsules of nearly primordial gas, we find about 3 times less lithium-7 than Big Bang nucleosynthesis predicts. This cosmological lithium problem has vexed cosmologists for decades. Is it a sign that our understanding of how stars process lithium is incomplete? Perhaps these ancient suns have mechanisms that slowly destroy the lithium at their surface. Or could it be something more profound, a hint of new physics beyond our standard model, some unknown particle or interaction that was present in the early universe? altering the lithium abundance while leaving the others untouched. This unsolved mystery doesn't invalidate the theory. On the contrary, it sharpens it. It provides a focal point for future research, a loose thread that, when pulled, could unravel an even deeper understanding of the cosmos. It reminds us that science is a living, breathing process of inquiry, not a static collection of facts. The overwhelming success with helium and deuterium provides such a powerful foundation that we can use it to probe for new discoveries, confident that the core of the story is correct. The agreement is simply too good, too precise, across too many independent lines of evidence to be a coincidence. And so we stand here today, no longer with a mere speculation, but with a cornerstone of modern cosmology, verified in the great celestial laboratory. The journey took us from the abstract world of nuclear physics to the most distant shores of space and time. We learned to read the atomic fingerprints left behind in the ghostly light of quasars, and to assay the chemical content of galaxies we can never hope to visit. We performed forensic science on the universe itself. The verdict is in, and it is unequivocal. In those first few minutes, under conditions of unimaginable heat and density, the universe did indeed forge the raw material for everything that would follow. The hydrogen that fills our oceans and fuels our sun, the helium that lifts our balloons and makes up a quarter of the visible cosmos, these are the direct tangible relics of the Big Bang. The primordial elements were now in place. The cosmic recipe had been written, and the ingredients laid out across a vast, expanding and cooling universe. The stage was set. But for hundreds of millions of years, this stage would remain dark, filled only with this simple, transparent gas. The grand complex story of cosmic structure of galaxies, of stars, of planets, and of us was yet to begin. The universe was waiting for gravity to slowly, patiently gather these first atoms together, waiting for the darkness to be broken by the first light from the first stars, and so the cosmic fire subsides. The universe, for the first time in its brief, violent existence, takes a breath. In a span of time shorter than it takes to brew a cup of coffee, the greatest act of creation the cosmos would ever know has reached its conclusion. From the searing, undifferentiated energy of the first second, an astonishing and elegant simplicity has emerged. We have journeyed through that furnace, through the quantum chaos and the temporal fog, to witness a moment of profound transformation. A moment where the fundamental laws of physics, etched into the fabric of reality, conducted a perfect and unrepeatable symphony. There was no conscious design, no guiding hand, only the inexorable dance of temperature, density, and time. The result was not a chaotic jumble of particles, but a universe endowed with a foundational chemical structure. A universe composed almost entirely of hydrogen and helium. This wasn't just a cooling, it was a crystallization of matter. The protons and neutrons, once a frenetic soup, were now bound by the strong nuclear force, locked into stable configurations that would endure for eons. Think of the sheer, breathtaking efficiency of it all. For every single neutron that existed when this process began, almost every single one ended its journey, sheltered inside a helium-4 nucleus. A particle that left on its own would have decayed into nothingness in mere minutes, was instead preserved, becoming a cornerstone of the future cosmos. The universe, in its own primal way, demonstrated an unparalleled economy, wasting almost nothing in its quest to build the first atomic nuclei. This brief incandescent period of nucleosynthesis wasn't merely an event. It was the universe writing its own origin story into the very substance of its being, and the most incredible part is that it left behind the evidence, a cosmic fossil record of unparalleled clarity, waiting billions of years for a species on a small rocky planet to learn how to read it. This is perhaps the most powerful legacy of Big Bang nucleosynthesis. It is not just a theory of how the first elements came to be. It is a tool, a cosmic probe that allows us to reach back across 13.8 billion years and measure the precise conditions of our own genesis. It provides one of the most stringent tests of the entire Big Bang model, a pillar of modern cosmology that stands firm not on faith, but on verifiable quantitative prediction. The key to this incredible forensic power lies in the abundances of the light elements themselves, particularly in an isotope we've seen play such a critical role, deuterium. Deuterium, that simple nucleus of one proton and one neutron, is the ultimate cosmic barometer, Its survival was a delicate, precarious affair. It was the essential stepping stone to creating helium, yet it was also incredibly fragile, instantly destroyed by the high-energy photons that saturated the young universe. Only when the cosmos cooled enough could deuterium survive long enough to fuse. This delicate balance makes its final leftover abundance exquisitely sensitive to one crucial number: the density of normal baryonic matter in the universe. Imagine a vast, crowded ballroom. If there are many dancers, partners find each other quickly. In the early universe, if the density of protons and neutrons was high, deuterium nuclei would rapidly find partners and fuse into helium, leaving very little deuterium behind. The reaction would be ruthlessly efficient. Now imagine a sparse, empty ballroom. Dancers might wander for a long time before finding a partner. If the cosmic density were low, deuterium nuclei would have fewer opportunities to collide and fuse. The process would be less efficient, and a much larger fraction of deuterium would survive the era of nucleosynthesis untouched. So by measuring the amount of primordial deuterium we see in the universe today, by looking at ancient gas clouds so pristine they are untouched by stellar processing, we are in effect weighing the universe at 3 minutes old. It is an astonishing feat of scientific deduction. The measurements from these distant clouds captured by our most powerful telescopes give us a precise value for the baryon density, and that value matches with breathtaking accuracy the value derived from a completely different method, analysing the faint residual afterglow of the Big Bang itself, the cosmic microwave background radiation. Two entirely separate windows into the early cosmos, one looking at the universe at 3 minutes, the other at 380,000 years, give us the same answer. This is not a coincidence. It is the resounding affirmation that our understanding of the cosmic story is fundamentally correct. The universe is consistent with itself, and we are capable of deciphering its language. But the fossil record tells us even more. It speaks not only of the universe's contents, but of its behaviour. The final abundance of helium-4 acts as a celestial speedometer, a relic that records the expansion rate of the universe during that critical period. The entire process of nucleosynthesis was a frantic race against time. Neutrons were decaying and the universe was constantly expanding and cooling, which slowed down the nuclear reactions. A faster expansion would have meant the universe cooled more quickly. The window of opportunity for fusion would have slammed shut sooner, freezing the process with more neutrons left unfused, resulting in more leftover deuterium and less helium-4. A slower expansion, conversely, would have allowed the nuclear furnace to burn for longer, giving the reactions more time to run to completion, converting virtually all available neutrons into helium and leaving even less deuterium. Our observations of primordial helium abundance therefore place a strict constraint on how fast the universe could have been expanding in its infancy. This in turn allowed cosmologists to make one of the most stunning predictions in all of science. The expansion rate was governed by the total energy density of the universe, and a significant part of that energy was in the form of radiation, including the ghostly particles known as neutrinos. By using the observed helium abundance to calculate the expansion rate, physicists in the 1970s predicted that there could only be 3, or at most 4 families of light-stable neutrinos. More families would have meant more energy density, a faster expansion, and a helium abundance inconsistent with observation. For decades, this remained a powerful but unverified prediction from the dawn of time. Then in the 1990s, particle accelerators like the Large Electron Positron Collider at CERN, smashing particles together here on Earth, measured the properties of fundamental particles with incredible precision. Their findings were unequivocal. There are exactly 3 families of light neutrinos. The universe, in its first 3 minutes, had whispered a fundamental truth about particle physics, a truth we would only be able to confirm with our most advanced technology 13.8 billion years later. The very large and the very small were connected in the most profound way imaginable. Yet for all its spectacular success, our story is not quite complete. Like any great fossil record, the one left by the Big Bang contains mysteries that continue to puzzle and inspire us. There are still faint whispers from that primordial era that we do not fully understand, and the most persistent of these is the cosmic lithium problem. Our models of Big Bang nucleosynthesis, the same models that predict the abundances of deuterium and helium with such stunning accuracy, also predict the amount of lithium that should have been created. specifically two isotopes, the more common lithium-7 and the much rarer lithium-6. The theory is clear, it gives us a number. But when we turn our telescopes to the oldest, most primitive stars in our own galaxy, ancient relics that should preserve the primordial abundances of the elements, we find a disturbing discrepancy. These stars contain only about 1/3 of the lithium-7 that our theory predicts they should. Where has all the lithium gone? This is one of the most significant unsolved problems in cosmology, a tantalizing clue that our story is missing a chapter. The solutions fall into 3 broad categories. Perhaps the problem lies not in the distant past, but in the stars themselves. It could be that our understanding of stellar physics is incomplete. Perhaps these ancient stars over their long lives have mechanisms that efficiently destroy lithium, transporting it from their cool surfaces down into their hot interiors where it is burned away. Astrophysicists are working tirelessly to model these processes, trying to see if they can account for the missing element without breaking our well-established theories of stellar evolution. It's a difficult and complex challenge trying to read the biography of a star billions of years old. A second, more profound possibility is that the issue lies with our understanding of the Big Bang itself. Could there be new physics at play, something happening in that primordial furnace that we haven't accounted for? Perhaps the decay of some exotic undiscovered particle during or after nucleosynthesis altered the final abundances. Maybe the fundamental constants of nature were slightly different then. These are speculative ideas pushing the boundaries of known physics, but the lithium problem forces us to ask these deep, unsettling questions. It reminds us that our standard model of cosmology, for all its triumphs, may still be an approximation of a deeper, more complex reality. The universe may yet have secrets to reveal about its own birth. Or finally, the problem could lie with our observations, though this is considered the least likely explanation, given the consistency of the data from many different stars. This unresolved tension is not a failure of the theory. It is the very essence of the scientific process. It is a sign of a healthy, vibrant field of inquiry. The lithium problem is a loose thread in an otherwise perfectly woven tapestry, and pulling on it may unravel a deeper understanding of the cosmos. And our quest for understanding doesn't stop there. The precision of our cosmological measurements is becoming so extraordinary that we're using the primordial elements to probe the nature of neutrinos themselves. By refining our measurements of deuterium and helium, we can place even tighter constraints on the expansion rate of the early universe. This in turn can help us answer fundamental questions in particle physics. Could there be a fourth sterile type of neutrino that doesn't interact with other matter except through gravity? Such a particle would have contributed to the universe's energy density and affected the expansion. Precise BBN calculations can help us hunt for the subtle signature it might have left behind. We are entering an era where cosmology and particle physics are no longer separate disciplines. The entire universe has become our laboratory, and the first 3 minutes are our grandest experiment. And so we bring our journey full circle, from a maelstrom of pure energy to a cosmos filled with the raw materials for future grandeur. It is a story of profound simplicity giving birth to staggering complexity. After the fury of nucleosynthesis ended, the universe entered a long quiet period, a period sometimes called the Dark Ages. The cosmos was filled with a vast expanding and almost uniform fog of hydrogen and helium gas. There were no stars to pierce the darkness, no galaxies to pinwheel through the void. There was only this simple primordial inheritance, but it was enough. This raw material, this chemical foundation forged in the first 3 minutes, was the seed. It was the essential ingredient from which everything else would grow. Gravity, the patient sculptor of the cosmos, went to work on this gas. Over hundreds of millions of years, it patiently gathered these primordial atoms together. It pulled them into ever denser clouds, vast nebulae that would eventually collapse under their own weight. And in the hearts of these clouds, the pressure and temperature would rise once more until they reached the point of ignition. The first stars were born, shattering the cosmic darkness. And these stars, born from the hydrogen and helium of the Big Bang, began the next great chapter of creation. In their nuclear cores, they fused those light elements into heavier ones. They forged the carbon, the oxygen, the nitrogen, the iron. The very elements that make up the ground beneath your feet, the air that you breathe and the complex cells that constitute your own body. When you look up at the night sky, every single point of light you see, every star, every galaxy, is a direct descendant of that first brief creative fire. Every structure in the universe is built upon that simple foundation of hydrogen and helium. The atoms that form your own consciousness, the carbon in your DNA, the calcium in your bones were forged in stars that could only exist because the Big Bang first provided the fuel. The story of nuclear synthesis is therefore our story. It is the first chapter in the grand narrative of cosmic evolution that leads in an unbroken chain from a hot dense plasma to the silent observer contemplating the stars. We are in the most literal sense the universe's way of understanding itself. We are stardust contemplating the fire from which the first atoms were born. The echoes of that creation are all around us and most profoundly within us. The journey from then to now is the story of everything, and it all began in the first 3 minutes